Okay, so there's a couple of things that are not specifically done in the textbook, but if we don't talk about them now, then you don't get to see them until like the fourth year class. So let's just go ahead and revisit. Because it's an extension of what we already know. And the thing that we already know we know two things, three things maybe. We know phase diagrams, pressure versus temperature plots, and we know Raoult's law that the vapor pressure above a solution is dependent on its composition. And we know Henry's law that the vapor pressure above a liquid is dependent on the amount of dissolved component in that liquid. Okay. Those are all going to make a revisit. Okay, so in a phase diagram, we plot pressure versus temperature. And the simplest thing is to think about this in terms of zones or regions, that what phase of matter will exist when temperature is low and pressures are high.
When temperatures are low and pressures are high,
Yes.
solid.
So we're looking at solids being somewhere in this zone, and when pressures are low and temperatures are high, gases exist somewhere here, and that means that liquids exist somewhere in between. And we know that the boundary, the transition between solids and liquids is a definite number, and it's an intensive number. So it doesn't matter what scale you use to generate this. If we do it on a 100-gram scale or a 100-kilogram scale, the transition between ice and water is still 0 degrees Celsius. And it's 0 degrees Celsius in that direction, and it's 0 degrees Celsius in that direction. So there is a point. These transitions, however, are not linear. That one is the most linear. We have three points of demarcation that separate the world of the solid from the gas, from the world of the solid from the liquid, and the world of the liquid from the gas. This is what we call the sublimation curve, because sublimation is the transition from solids directly to gases. From gases back directly to solids is called deposition. But we just call that the sublimation curve. The transition from solids to liquids is called? If you had a solid and you warmed it up and you made it turn into a liquid, what have you done to it? You've melted it. So that should be the melting curve. Only we have another word for melting that predates well, that's the fusion curve. And the fusion curve is usually the most linear of the three curves. And then this evaporation part right here, that's your condensation curve. Okay.
Condensation is from gas to liquid.
Yes. Yeah. Actually, liquefaction is from gas gas to liquid, that's the proper word. Yeah. Don't like condensation because condensation is used in another sense. In organic chemistry, a condensation is a reaction that generates a small molecule as well, gives you a product, and then pops off a small molecule as well, usually water, therefore condensation, but could easily be an ammonia or something like a methanol. Okay. This is a normal phase diagram for something that is pure. And I'm saying normal because it's describing, this shape describes lots and lots of things. It can be distorted in all different ways, in that some material might not have much of a solid, might have lots in the gas, whatever. This part right here, the triple point, where all three solid liquids and gases coexist, could be anywhere on the diagram, but it has to be somewhere. Okay. But normal is a word that also has multiple meanings. We used normal last week to talk about refractive index. That normal means perpendicular to the surface. Normal also means atmospheric conditions. So if I find myself the part on this phase diagram where the pressure is atmospheric pressure, then normal behavior happens at atmospheric pressure. So I'm going to read across here. And where the line intersects between solids and liquids, if we read down, this gets to be normal melting point. I'm going to use the word temperature because melting temperatures are not melting points. There's always a range. The narrower the range, the more likely you are to be pure. Purity is associated with phase transitions that are narrow in temperature and high. And then this gets to be normal boiling point. Okay. And then we can do all the usual stuff. We know that in the world of solids, particles are close packed. Density is high. In the world of liquids, the particles are removed from each other somewhat, but not beyond the point of attraction. So our intermolecular attractions exist. And when one thing moves, it will have an effect on the other. And then in the world of gases, the distance between the gases is significantly larger than the size of the particles themselves. So, and no attractions. They only have attractions and appreciable volume if they're real gases, not ideal gases. Okay? So, if I take a solid and without changing its pressure, I heat it up. I give it more kinetic energy. I make these vibrations larger, I loosen the shackles, give these more space, but don't break the molecular interactions. It becomes a liquid, keep heating it. I break the molecular interactions and let those now enter the gas phase. Makes complete sense. And the opposite way. And then, if I take a gas, and without changing the temperature, I pressurize it, maybe by containing it into a smaller volume, it becomes a liquid. And then, as I continue to pressurize, it becomes a solid. This is normal behavior. It is not the behavior of water. Water has a fusion curve that bends this way, to the left.
So, it would go from, if you were to pressurize it without going, it would go from gas to solid to liquid, depending if it's a lower.
There is a point where you can,
That's weird.
this is something that you already know, that if you have a layer of ice and you step on the ice is very, very slippery. In fact, if you were to put all of your body weight, not just on the ice, but through an ice skate, then the skate takes all of your weight, pressure. Underneath the skate is not ice, it's liquid water. And you glide on that surface of liquid water.
That's sick.
I have an experiment with the big block of ice and the wire and the weights, and you put the weight over the piano wire over the block of ice, and the wire goes through the ice. Have you seen that? Did we do that for you when we were in chemistry 1?
Oh, you weren't my lab.
No, I did it in class.
What?
It makes a mess because the ice melts at room temperature.
No, you didn't.
So you need to put lots of towels down. We did it between 2 desks. We found a gap between the 2 desks. I still got the block of ice, it's in the fridge. And I got the weights and the piano wire. We'll do it in the lab on Thursday, so you can see it. So if we have a block of ice, and I've got 2 big heavy weights, and a piece of piano wire, and the pressure, the weight pulls the wire down, and because this is ice, you pressurize it, and underneath the wire turns into liquid. So the wire drops into the liquid, and it pressurizes the ice, which turns into liquid, so it drops. And over the course of a couple of hours, at some point, the wire goes right through the center, and above it is ice, and below it is ice, and the wire goes right through the middle.
Wow.
And then after a while, the wire drops out, and the weights clang to the floor, and the block of ice is still intact. Because when you take away the pressure, it goes back to being ice, because it's cold. Okay. Water is not a normal representative liquid. When we say to humans, okay, explain to me what liquid behavior is, and they start to tell you about water, because they've been around liquids all their life. Gosh, they live near the coast. They know nothing about liquids. They know water behavior, and water is atypical. Ice floats because ice is less dense than liquid water. Solids are less dense than liquids, but ice is less dense. Because its phase diagram is wrong, its fusion curve tilts the wrong way. And it's a good thing, because
Yes.
if it wasn't tilted the wrong way, there would be no life on this planet.
Mhm.
It would not be possible. Okay. This is what we know. We also know so before I get to this, let me talk about one more thing. Freezing and melting happen at the same time, at the same temperature, and boiling and condensation happen at the same time, at the same temperature, and they are intensive. What does that mean?
It doesn't change amount.
They're completely independent of amount. So it doesn't matter what scale we do it on, we still get the same number. Okay, so at atmospheric pressure, water, not a typical liquid, but this part of its phase diagram is typical, boils at 100 degrees Celsius. What's actually happening? So here's beaker, and here is a heat source, Bunsen burner, right? And I give the liquid enough kinetic energy that it sends particles into the gas phase. Okay. And when it does, it takes the energy with it, which is why the temperature never rises at the thermometer, because when the enthalpy of vaporization takes the energy with it. Okay. So temperature doesn't change during a phase change. Those are intensive. This resistance from going from the liquid to the gas, the resistance against that is atmospheric pressure. It's the pressure of the atmosphere pushing down on the surface of the liquid. Okay. So here's us in South Texas with a little beaker making water boil at 100 degrees Celsius. And then we wander into New Mexico, where we start to get mountainous. And we go up the Sangre de Cristo mountains, and you boil water up there, and it doesn't boil at 100 degrees Celsius.
Increased pressure.
Increased pressure.
Or is it decreased pressure?
Atmospheric pressure is the mass of all of the gas particles in all of the atmosphere being pulled down by gravity to the surface. When you are up in the mountains, there's less. I got all of the coast, I've got all of those that are not represented when I'm up in the mountains. So atmospheric pressure is lower at altitude than it is at sea level.
So why is it harder to
Less resistance, less resistance to boiling. This is my normal temperature. When I go up in altitude, my atmospheric pressure drops. And I slide down this curve, and now my water boils at 90 something instead of 100. Okay? I used to live at 5,770 feet of altitude. And, no, is that right? Maybe it's the other way around, 7,000, no. Taos is 7,000, I used to live in New Mexico. 5,770 feet, and water boiled at 92 degrees Celsius. Yeah. We got a beaker out once in the lab, and we boiled water, and went, look, it's 92. And everyone looked at me like, what? Because they didn't know that it was supposed to boil at 100. Okay? So, these values depend on pressure. That's why you've got these curved lines. That's what they represent. When something is pure, those numbers, the normal values at atmospheric pressure, are characteristic. So if you give me a compound and say, this is acetanilide, and I don't believe you, I would just stick it in the melting point apparatus, melt it, and it would tell me that its melting point is a specific number. And then I would go look it up in the textbook, in a reference book, like the rubber book that we saw a week ago. And if my number and the book's number were different, then what you've got was not acetanilide. Okay, because melting and freezing and boiling and condensing are characteristic values. But they're only characteristic when they're pure. This is where colligative stuff comes in. When you add an impurity, you change the shape of this phase diagram. Okay. Now, water is not a suitable example in all cases, but it's good enough, right? Especially at this part. Maybe not so much down at that part. If I wanted water to boil at a higher temperature than it currently is boiling, I can do two things. I can put a lid on the pan and trap the pressure inside the vessel. And now it has to fight harder to escape. And therefore, because it's trying harder, it accepts more heat and the temperature goes up. That's how pressure cookers work. You increase the pressure. If you increase the pressure, you drive me up this line. Okay? Or you could add an impurity. If you add salt to water, you've got a boiling water on the stove in a pan and you throw some salt in it, it stops boiling. It starts accepting more heat, and then when it boils again, it's now boiling at a higher temperature than it was before. It causes the boiling point to be elevated.
For all?
Everything. Everything. Because this is a physical property. In order to boil, here's my liquid. Boiling doesn't happen at the surface. Boiling happens throughout the entire substance. Evaporation happens at the surface. Evaporation can only happen at the surface And evaporation is when we turn a liquid into a gas below the boiling point, below the temperature threshold. So I'm going to make that liquid escape and be a gas. But I've added an impurity. Those impurities just get in the way. They just now physically in the way of the liquid getting out. And for exactly the same reason, when there's ice in the driveway, we throw salt on the driveway because it causes the salt to melt. Because salt is going to make the water in your driveway freeze at a lower temperature than it normally would. And if it's only -1 or -2 degrees Celsius outside, and you can salt it so that your salt water wants now to freeze at -5, your -2 ambient temperature is now not cold enough to make the salt water freeze. And freezing happens when this particle, molecule, makes connections, makes interactions, and locks in a three-dimensional lattice structure with the molecules around it. And when there is an obstacle in the way, this cannot attach to that. It just makes it harder. So by adding an impurity, you make it harder to boil, more temperature goes up, and you make it harder to freeze. Temperature goes down at the other end too. Okay, what would that look like on our phase diagram? What would it do to the curves?
It would like spread out, right?
Mm.
Kind of, sort of, ish.
If I add an impurity, think about this for a second. Well, let's limit ourselves to the normal part, just where it's 1 atmosphere. What happens right here?
Ships out.
Yeah, now when it boils, it might boil there. And when it freezes, it might boil here. So we get this kind of phantom phase diagram that lays on top of it, where it splays out. Colligative properties, I'll let you catch up. Colligative properties are the exact opposite of intensive properties. I'm not actually 100% sure what happens here. I think, I don't know that sublimation, if it is affected, I don't think it's affected to nearly the same extent. So what I'm going to do is I'm going to have these still meet a kind of triple point, and then whatever's deviating here, I don't think it's by much. I don't think that we see quite the same effect in the sublimation. where is our elevated boiling point? And this is our depressed freezing point. Intensive properties are independent of amount and only depend on the material. So they depend on identity of the material, not on its amount. Colligative properties are the exact opposite. Depends only on amount. Not on the identity. And there's plenty to look for. Even in our General Chemistry 1 textbook, there's a couple of famous experiments out there that lots of people do in General Chemistry lab about depression of freezing point. That they'll find something that has a known, they'll take something that's pure, they will find its freezing point, then they'll add an impurity to it and watch it become more difficult to freeze and move to a lower freezing point. And then, even though this says it doesn't depend on identity, they'll tell you what it was that you added. Because when we say it only depends on amount, what that actually means is not mass, it's the molar amount. It only depends on how much you actually add. So we add salt to make ice melt. Now if you didn't have salt, you didn't have sodium chloride, and you use potassium chloride, it would work exactly the same way. If you wanted to put salt into your boiling water pan at home while you were cooking, and you didn't have any sodium chloride, because you're cooking at your granddad's house, and he's not allowed to have sodium chloride, he's got potassium iodide in his, he's got iodized salt, with the low sodium one. Exactly the same effect, okay? But it's the exact same effect when you have a mole of this and a mole of that. Not a gram of this and a gram of that, okay?
Dr. Boyd, what about it's like geometry, how some things can be like tetrahedral, octahedral, stuff like that, like the different holes or spaces, does that affect anything? How well it melts or not?
Yeah, so this is just the ground floor. You've asked me to hurt you. There is so much more. I have a little book in my office that is the Little Book of Phase Diagrams. Hold on. Because things have different morphologies. And the big one out there that I really don't know nearly enough about is minerals. That minerals exist in a multitude of forms, and each mineral has its own name depending on what shape it looks like. Oh. I'm looking for a book on a shelf and I'm not wearing my glasses, I won't be able to find it. I'll be right back.
Sorry, I will. I swear, just one day. One
The
day.
inorganic is one, I hated the shapes, but like, we talked about like if you have, an impurity, and then like if you remove So that's why I was asking. Okay.
No, we started talking about liquid earlier, and I'm like, I haven't heard of that in a minute, or at all.
What's it called? So Kat, what is, this is gonna be a really dumb question, what is chemical engineering? What is that?
Good question. It's like it's, I guess, manipulation. I think it's kind of like manipulating chemicals, but I could be wrong. I know, there's multiple, I know, like, there's tons of different ways. Let's look it up. Cause like, I wanna be a pharmaceutical engineer.
Oh, okay.
So I
okay.
wanna make meds, and I feel like I can do that, and most people are chemical engineers.
That's cool. I was telling my mom, like, there's also chemical engineering. I'm not trying to do that.
You're
She was all like, what is that? I was like,
Develop and design chemical manufacturing processes. Apply the principles of chemistry, physics, and engineering to design equipment and processes for manufacturing products, gasoline, detergents, and other things. Yeah. How to design processes to produce, transform, and transport materials.
He said he asked me to touch you.
Took a while to find because I remembered this book being green. No, it's not green, it's actually black. And I also remembered it being completely chock full of phase diagrams. And it's really not. This is a book about phase diagrams of the elements. And yeah, okay. So this is helium. Okay, it's a little bit different than what we're looking at. For those of you playing along at home. This is a bit different. And this is oxygen. And what's happening here is this is no longer simple. It's no longer simple in that there's more than one morphology. There's more than one shape for the condensed forms. And let's find, that's bismuth. Bismuth is a metalloid, it's shiny, very highly crystalline. If you've probably seen it. It's bismuth. Rainbow colors, and it's in geometric block shapes. If you did a quick Google search for bismuth, you would see it. And then something like antimony. Nice and simple.
Oh, yeah. Oh my goodness.
Yeah.
That is so
Let me hold that up so the other camera can see it. That's what bismuth looks like. Polycrystalline.
That's cool. Can I see that? Oh, never mind. You already looked it like
And then things that are, there you go, barium.
Oh.
This one actually labels it with notations that you will know, that there's a hexagonal morphology in there, and there's a HCP, which means
Bring it back to me.
hexagonal close packed.
Oh.
Okay. And then BCC,
Something cute.
body-centered cubic. So we go from body-centered cubic, which has a coordination number of 8, to hexagonal close packed into hexagonal. and then the liquid over here on the other side. So this is the simplistic sense, okay, just to get a sense of pressure to temperature relationships. But yeah, if there's allotropes, that the allotropes are elements that can exist in more than one form, then yes, they all coexist on the same map. Think of this as a map, okay? We've just introduced two things. By introducing an impurity, this is now a phase diagram that contains two things. This is salt water, or something dissolved in something else, okay? So what we need to do next is revisit the part of science that we already know, that is two things occupying the same space. Simple liquid mixtures, okay? And then we will adapt that to be liquid mixtures that disobey the rules. And then once you venture into solids, solid mixtures that occupy the same space, then it gets kind of complicated because you're looking at alloys, and the phase diagram of an alloy can be all over the place, the same way that the phase diagram for a mineral will be. If you ever want to shock, look up like the phase diagram of glass. Or yeah, some of them are really, really complicated.
Why is it like
That you have little compartments that only exist at this. Yeah, yeah.
Exactly.
What is that one?
Why is it calculus?
Is that glass?
Yes.
We're going to see a little bit of this. This is a phase diagram of glass. See the thing where it points down and then dips back up?
Yeah.
We'll explain what that is.
Really?
But we won't explain what all the little compartmentalization is.
Okay. You can only handle one thing at a time.
The dip is called a eutectic, and
Is that the surface? It's not a real surface, but it's like the, is it like a surface between two things?
Sure.
Wow, Dr. Moore.
How do you spell eutectic?
Oh, we'll get there. Eutectic. Eutectic.
He started with an E, like,
I was like, hold up.
All right. So, how can we look at this and it not be completely overwhelming? Okay. So what we have to do is we have to pick and choose a couple of things that we can understand, and then we can delve just a little bit lower, because any further gets to be, this is professional levels of information in the phase diagram for that particular type of glass. Ideal liquid mixtures obey Raoult's law. What does Raoult's law tell us?
Something with gas, I forgot.
Something,
Can you even hit it?
something gas.
Yeah.
The
How about I don't avoid
pressure of a mixture is equal to the pressure of the first component plus the pressure of the second component.
Oh,
Wait, is it a fugacity something thing?
I don't think we could turn this into a fugacity thing and not allow the vapor pressures.
That's what that was.
But this is a weighted average.
Unless the X's mean what?
Mole fraction.
Right.
So I have two gases, A and B, and XA is the mole fraction of A, which is the number of moles of A divided by the total number of moles. And because currently I'm limiting myself to two components, currently limiting myself to two components, the total number of moles is NA, number of moles of A, divided by the number of moles of B. This gives me a value, a range of mole fraction that is from 0 to 1.0. It's a percentage, except it's not out of 100. If I multiplied this by 100, it would be a percentage. Okay. Let's look at this. If I had a sample, and that sample contained no gas, none, what would the pressure of that gas be? Yeah. So I am tied down on my, is this the X or the Y?
Why?
Just checking.
Okay.
I had, every now and then I check in on the first year chemists about which one is X and which one is Y. Because, sometimes you need to be reminded. If I'm measuring pressure up on this scale, and I'm measuring amount on this scale, when I have 0 number of moles, there ain't no pressure.
My taxi really came out like my bad.
And when I have all the gas, but that's the only thing that there is, then I have the vapor pressure of this gas. Okay.
And then if you have it like, you compared them and then there was like a dip and something.
Yes. Yeah. So what I'm actually measuring is not the pressure of a gas per se, but the pressure of the vapor. So here's a liquid. It's in a beaker, and some of that liquid is escaping to be in the gas phase. If I opened a bottle of gasoline, it wouldn't take you very long to be able to say, I can smell gasoline, because it's very volatile, that the liquid leaps out into the gas phase. That's why we burn it, because it's very good at burning. Whereas if I opened a bottle of dimethyl formamide, that's got a pretty low volatility, you probably wouldn't be able to smell it from a distance. It wouldn't fill the room up with the vapor. Okay, so those two have their own inherent vapor pressure, even though they're completely pure. All right. So what I'm going to do is measure this pressure, the pressure of the vapor coming off the liquid. And when there is no liquid, there can be no vapor from that liquid. And when there is only this liquid, then you get its vapor pressure. And that should be a straight line.
Should.
Uh-huh. Okay. Let's call that one A. And if I read mole fraction of A, it does this. That when there is no A, I get no pressure. And when there is A, I get its vapor pressure. Okay. And then onto this, I'm going to plot B. Now, there is absolutely no reason to expect that B has the same volatility as A. So the vapor pressure of B, when I plot this, its mole fraction runs the other way, but follows the same trend. And Raoult's law just says those two numbers are additive. And that the vapor pressure of any ideal solution of two volatile liquids is those numbers added together. Okay, so let's say I want here, where it is maybe 1/10 of A and 9/10 of B. That you take that amount and then you add, so you take that amount and then you add that amount to it and you get this amount. They're just straight additive. And then we remember that there were deviations, but that's for when it's ideal. Ideal solutions happen ideality means that there is no interaction between component A and component B. Yes, they occupy the same space. Yes, they are soluble or miscible because they're both liquids. We use the word miscible, not soluble, for liquids. Solids are soluble in liquids. Gases are soluble in liquids. Liquids are miscible in liquids.
You don't
If you
pronounce
said,
the C.
no,
Sorry.
no, you don't pronounce the S.
I've heard people say miscible. This is miscible.
Miscible.
Just like M-I-S.
But then you said you were pronouncing the C and not the S.
He was joking.
He was
He
saying,
was
I was about to say.
I know.
The C in bucket is silent. two deviations from Ralph's law. One's what we call a negative deviation. This happens when A and B are attracted to each other. This would happen when this is polar and that is polar. Or really specifically, when this is protic and that is protic. Do we understand what protic means? Hydrogen bonds exist between adjacent molecules when there is a hydrogen directly attached to an electronegative atom. So alcohol and water are both polar protic molecules because they have a hydrogen that's attached to an oxygen. But that oxygen also has lone pairs of electrons, and you end up making a hydrogen bond from the lone pair of electrons on one molecule to the hydrogen of the other, and they go in a straight line. And the way that they classify hydrogen bonds is backwards, that the hydrogen is the donor and the lone pair is the acceptor, which is completely backwards to the way that we think of all other bonds, as the lone pair of electrons is the base, which makes the bond and reaches out. Mm-hmm. And we used hatched lines, not dashes, not a dash, hatched lines to describe that. Okay, if the two molecules are attracted to each other, then they hold on to each other and don't let the molecules escape into the vapor. Do you remember that time where we took a graduated cylinder of alcohol and a graduated cylinder of water and mixed them together?
Yes.
And the volume was not the same.
It was weird.
Remind us to do it in lab on Thursday. We'll do it again. The actual physical size of the solution will shrink because this alcohol is only capable of making one hydrogen bond because it has one hydrogen, whereas a water is capable of making two. So when you add water to alcohol, you make it better at sticking together, which means it doesn't escape into the vapor anymore. And we get a sag here. That's a negative deviation. In a positive deviation, A and B repel each other. Now, there's a limit here, because if they repel each other very, very much, you'll make two layers. You'll make an immiscible mixture of polar and non-polar, and the oil and water won't mix. So there's a limit that one of these is going to be polar and the other one is going to be non-polar, but they cannot be highly polar and highly non-polar. It has to be within a reasonable range, that one of them is not very polar and the other one is also not particularly inclined one way or the other, but they don't match. Okay. And in that case, because now they don't want to share the same container as each other, they want to escape into the gas phase, and we get a bulge out the other way. So this is a positive deviation up top, and this is a negative. And then there's something special, and here's where we learned the first completely new thing, just in time to be done. Sometimes you mix two things together and they form a special deviation that's called an azeotrope. And an azeotrope can be up or down. But what happens in an azeotrope is that the vapor pressure of the mixture refuses to change. Yeah, and there's a very, very famous one. Okay. And we'll plot it, we'll do more of this, because we've got to do azeotropes and eutectics belong in the same conversation. They mean different things, but they share an awful lot in common. All right, let's look at this. Here's ethanol. Ethanol is the alcohol that is generated from the fermentation of fruit. So wine, alcohol, and like vodka, whiskey, right? Well, I've drawn it linear. It's not linear, it's bent. These two have an awful lot in common. They are completely miscible. They are both colorless liquids, not odorless, because alcohol has a smell, but they are both colorless. So if you had a bottle of alcohol with a lid on it so I couldn't smell it, and a bottle of water, and a bottle of alcohol and water, can't tell the difference. Can't tell the difference. They have different densities. So if I filled up a bathtub and threw all the bottles in the bathtub, they would float at different heights because they have different densities. And they have different volatilities. The boiling point of alcohol is 78 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So, that's 22 degrees Celsius difference between the two, right? So if I flame, hot plate, heating mat. Okay, if I put alcohol and water in there, the alcohol boils 22 degrees before the water does. So what comes out here should be 100% pure alcohol. Should.
Keyword.
But it's not. You cannot buy 100% alcohol. What's the strength of the whiskey that you buy in the store?
I'm under 21, but I remember you told us this. I forgot. It's not like 60%. Is it? No, that's too.
So there's two numbers. There's an actual percentage number, and then there's something called a proof.
Yeah.
And the proof is half of the, no, double what the percentage is. So if it's 80 proof, that means it's 40% alcohol. Yeah, that sounds about right. This is never going to come across as 100% alcohol. Let's say on the first pass, this is a simple distillation. Simple distillations work when the gap between the two boiling points is sizable. But let's just say this is still polar and protic. It's going to drag some water with it. Let's say that on the first path I get 80% alcohol. I would take that 80% and put it back into a new distillation and distill it again. And then distill it again. And then distill it again. And then distill it again. And after a while, I'm going to find out that the composition that comes over at the end isn't changing. That it won't go past 96%. It won't go past 95, 96%. Because it's formed an azeotrope. And an azeotrope is a mixture where the two components stick together in such a way that it is lower in boiling point. The mixture is lower in boiling point than either of the pure substances.
Either?
Yes. That if I plot, there's my 78, there's my 100, okay? I'm supposed to have a sliding scale that when I boil this, the first thing, the most volatile thing should come off first. And if I recycle it, I should just make it better and better and better. But this sags in a very specific way, something like that. And this right here just says, nah, no, I didn't do that well enough. It dips here. And this mixture is lower in boiling point. How are they going to do it? It's kind of like that. Is lower in boiling point than either of these two, which means you are fighting a losing battle. That's why we can't buy 100% alcohol, because you can't distill the water away from it. And if you start reading the billboards and the magazine articles about the local made gin in town, what's that called? Deep Eddies? Was that vodka? Vodka. It says triple distilled for purity. That's marketing speak for we gave up. Because after the third, you do it 4, 5, 6, 7 times, you still come back to the same composition every time. Every time. That the mixture is lower in boiling point than either of the two components that it came from. And we'll do the Ralph's Law things kind of easy. We'll do a couple of examples, but the big one that everyone needs to talk about is alcohol and water. And I'll dig up some examples. And then we'll look at eutectics. Eutectics are also a dip in the phase diagram. Okay. See